Let's look at three types of radioactive decay, and we'll start with alpha decay. So in alpha decay, an alpha particle is ejected from an unstable nucleus. And so here's our unstable nucleus, so uranium-238. An alpha particle has the same composition as a helium nucleus. So we saw the helium nucleus in the previous video, right? There are 2 protons in the helium nucleus and 2 neutrons. So I go ahead and draw on my 2 neutrons here. Since there are 2 protons, the charge of an alpha particle is 2+. So for representing an alpha particle in our nuclear equation, since an alpha particle has the same composition as a helium nucleus, we put an He in here. Right, and it has 2 positive charges, so we put a 2 down here, and then a total of 4 nucleons, so we put a 4 here. Trying to figure out the other product from our nuclear equation. I know nucleons are conserved, right? So if I have 238 nucleons on the left, I need 238 nucleons on the right. Well, I have 4 from my alpha particle, so I need 234 more. So 234 plus 4 gives me a total of 238 on the right, and so therefore nucleons are conserved here. In terms of charge, I know charge is also conserved. On the left, I know I have 92 protons, so 92 positive charges on the left. I need 92 positive charges on the right. We already have 2 positive charges from our alpha particle, and so we need 90 more. So we need 90 positive charges, and so we need an atomic number here of 90. So the identity of the other product, just look at a periodic table, find atomic number of 90, and you'll see that's thorium here. So thorium-234 is our other product. All right, so we think about what's happening visually, right? We're starting off with a uranium nucleus, right, which is unstable. It's going to eject an alpha particle. So an alpha particle is ejected from this nucleus, right? So we're losing this alpha particle, and what's left behind is this thorium nucleus. Right? So this is just a visual representation of what's going on here in our nuclear equation. All right, let's do beta decay. So in beta decay, an electron is ejected from the nucleus. And we saw in the previous video that you represent an electron, since it has a -1 charge, you put a -1 down here. Right? It's not a proton, nor is it a neutron, so we put a 0 here. So here's our electron, and an electron ejected from the nucleus is called a beta particle. And so we could put a beta here, right? And it's an electron, so a -1 charge, and then a 0 here. So if a beta particle is ejected from the nucleus of a thorium-234, right? So we're starting with thorium-234. This nucleus ejects a beta particle. So we go ahead and put a beta particle in here, so 0 and -1. What else is produced here? What else do we make? Well, once again, the number of nucleons is conserved, so I have 234 nucleons on the left. I need 234 on the right. I have a 0 here, so I need 234 nucleons. Charge is also conserved, so I have 90 positive charges on the left. I have 90 protons. On the right, I have a negative charge here, right? So I have a -1 charge, and so I must need 91 positive charges, because 91 positive charges and 1 negative charge gives me 90 positive charges on the right, and so I need an atomic number of 91. And so if you look at the periodic table, right, and you find the atomic number of 91, you'll see that this is protactinium. So we're going to make protactinium here, so Pa. All right, so what is happening in beta decay? Let's look at it in a little bit more detail. All right, so we already talked about the number of protons, right? So we have 90 protons on the left. How many neutrons do we have? Well, 234 minus 90, right? 234 minus 90 gives us the number of neutrons. So that's 144 neutrons. On the right, we have 91 protons. How many neutrons do we have? Well, that'd be 234 minus 91. So 234 minus 91 gives us 143 neutrons. So we went from 144 neutrons on the left to 143 neutrons on the right. And we went from 90 protons on the left to 91 protons on the right. So we lost a neutron and we gained a proton. So you could think about the neutron turning into a proton, and this is kind of an oversimplified way of thinking about it. But let's go ahead and write that down here. So a neutron turning into a proton. So a neutron has no charge, so we put a 0 here. So and a neutron is a nucleon, so we put a 1 right here. Right, so a neutron is turning into a proton, so let's go ahead and write our proton here. A proton has a +1 charge, right, and it's a nucleon, so we put a 1 here. So when we think about what else is made, right, we know that nucleons are conserved. So we have one nucleon on the left, one nucleon on the right. And so therefore, right, we would have a 0 here. In terms of charge, if we have 0 charge on the left, +1 on the right, we need -1 right here. And so this, of course, represents the electron. So this is the electron that's ejected from the nucleus. This is our beta particle. And also, actually, something else is produced. You're also going to make an anti-neutrino, and that's just really not part of this video, so we'll just ignore it for now. So a neutron has turned into a proton, right? And we're also getting a beta particle ejected from the nucleus. So when this conversion, this process is actually governed by the weak force, the weak interaction. And so there's a lot of stuff going on in a nucleus, which we just won't get into in this video. All right, so the important thing is to be able to look at a nuclear equation, recognize it as beta decay, and be able to write everything in your nuclear equation. All right, let's do one more type of decay. This is gamma decay. So gamma rays are given off, and a gamma ray has no charge and no mass. It's pretty much just energy. You could think about it. So these are pretty easy decay problems. All right, let's start with technetium-99m, and the M right here stands for metastable, which means a nucleus in its excited state. So nucleus in its excited state, so it has more energy. All right, so it's going to give off a gamma ray. So let's go ahead and draw on our gamma ray here, right? So 0 and 0. So since we're dealing with zeros, right, so these zeros aren't going to affect our numbers. So if we start with nucleons, right, we have 99 nucleons on the left, right? We're going to have 99 nucleons on the right. And in terms of charges, right, we have 43 positive charges on the left. We need 43 positive charges on the right. And since the atomic number isn't changing, right, it's 43 on the left, it's 43 on the right, we're dealing with technetium here. It's still technetium. It's just in the ground state, right? So it's no longer in the excited state. It's in the ground state. So it's given off energy in the form of gamma rays in this example here. And so technetium-99m is actually used in several medical imaging and diagnostic procedures because we have ways of measuring the gamma radiation. So this is very useful in medicine.